All right, let's talk about other things that people, various other things in the context of word embeddings that people have come up with as extensions of the base model. One of the things that people have considered in the last couple of years is to combine the classical word embeddings, which are just distributional models that are based on co-occurrence statistics on large data sets with classical lexical resources developed by linguists, right? So we have these classical lexical resources like WordNet or other things like the paraphrase database that give lexical semantic relations between words. For example, they could indicate a synonymy relation. And a synonymy relation means that two words have the same meaning. For example, big and large have very similar meanings, or fast and quick have very similar meanings. So in such a database would be stored that that these words indeed stand in such a relationship. And such databases are either compiled by linguists, so there's some human expert that can tell us, okay, these two words really have this lexical semantic relationship, or they can also be automatically compiled like from translation statistics. So if two words have to translate to the same word in another language, then probably they have very similar meanings. So there's a model brought up by Ferquay et al. 2015, which back at the time got the best paper at a big conference in NLP, where they try to combine both worlds, embeddings and lexical resources as follows. First of all, they have a lexicon of like n words, and for each of the words, they have, for example, a word-to-vec embedding given by qi hat. So this is a vector here, and then they want to learn new vectors qi. So the qi's pop up here again. So they want to learn new vectors, and these new vectors should have the property that they are similar to the original vectors. So we want to induce new vectors that are close to the original vectors that we have, and these original vectors are given by a distributional model. And again, you see here the square distance, and of course we want to minimize this sum here, right? And on the other hand, what do we have here? Here we have ij in our E. E is our lexical database. Maybe that's a synonym database. It says, okay, I and j stand in a synonymy relationship, right? And if I and j stand in a synonymy relationship, then their vectors should also be quite close. So here we have the lexical database. Here we have our word embeddings, and we want to induce new embeddings that satisfy both of these properties, close to the original embedding, embeddings, and they should be close if there holds a relationship in a lexical semantic database. And here we have some factors bij and alpha I. I think in the paper they set it all to 1. So this is here just for illustration that you can also weight this differently and then make weight the factors differently and put different importance on different factors. So that's the idea. Actually, that idea hasn't survived for a long time, and people are not really using that. But what has survived is this retrofitting, where you start out from something given and then you improve upon that, right? So this is also the case in many algorithms for bilingual embeddings, where they start out with monolingual embeddings and then they project them, they retrofit them into another space, so to speak. And of course, if you embed, what are you embedding actually? So you can embed characters, you can do embeddings of characters. However, there are no pre-trained characters on the internet. Why? So, or very few maybe. So why are there? So so this is also a very important aspect, because you have to keep in mind. That one purpose of embeddings is to overcome data sparsity. So the main problem is you have small labeled data sets, and you want to train a model from these small labeled data sets. So of course, at test time, new words come in which you have never seen. So without embeddings, you don't really know what to do with these new words, and your model would probably fail. So, but on the other hand, if you have word embeddings, you can leverage the full amount of data available on the internet by pre-training your word embeddings on these huge quantities of data, and then you have the property that similar words have similar embeddings. Therefore, if a new word comes in, you have that embedding for the word, and your model can deal with that word because it has maybe seen a similar word already. So that's a good thing. So you want to overcome data sparsity, and you leverage the knowledge of all of the net, of all of the web, so to speak, of all data on the web into your new data set on which you want to do classification, for example. Now with characters, that's really not necessary. I mean, at least in a basic setting, there are only like 40-50 characters in English. So there's no data sparsity. From any data set of like 2,000-3,000 examples, you see enough instances of each letter, like I, N, etc. Right? So there's no need to, at least not at the same scale, at the same magnitude of things, is there a need to get character embeddings. But you could go sub-character level. You could go into syllables. You split the words into syllables and then embed each of the syllables. Or you can do morphemes, where the difference between syllables and morphemes is that syllables are more structural units, like they depend on pronunciation, whereas morphemes are meaningful units. So you split a word into all parts that still have some semantics. So ing has some semantics because it is the gerund. Li has some semantics creedily because it makes out of the word creedy, and li means that becomes an adverb. Whereas with syllables, it's possible that you can split the words into parts that really are meaningless, right? And you can do, and for some languages this may be more important than for others. For example, for German, if you have a word like Dampfschifffahrt, that's very unlikely that you see such a word twice in your data set. So it's difficult to get an embedding for that word. But if you split that word into parts, then maybe it's rather easy to get embeddings for each of those parts. And the interesting thing is, so these are all things that are based on linguistics. So you have to have, this is a linguistic theory that explains syllabification. There's a linguistic theory that defines what morphemes are. But nowadays, like around 2016, 17, 18, and it has become popular to use so-called byte pair encoding, or word pieces also nowadays, that do the segmentation automatically from data. So you don't have to have a linguistic theory in the background, and you can do that for all languages. So this is byte pair encoding is an automatic process of splitting the vocabulary into smaller units, and it can be particularly important for some languages that have the property of building very long words, for example. What other things can we embed? We can embed n-grams. So n-grams, what are n-grams? So again, this is a language independent unit that just says we want to embed two, 3 or 4 units of the same thing. So n-gram is just a sequence of n units, and these units could be words. So we could want to embed 4 words. But what is more popular is we go on character level, and we embed 4 characters, for example. And this is exactly what fasttext has been doing. Fasttext has been quite popular, let's say between 2016 and 2018, because they were going on this subword level also, but without any linguistic theory in the background, such as syllables or morphemes. They were just saying, okay, let's represent each word as a bag of its character n-grams. For example, as it's 3 grams, 4 grams, 5 grams, and 6 grams. For example, where the 3 grams are, if you have the word where, then it would be represented as something like start of word WH, WHE, HER, ERE, RE, end of word, right? So that would be the n-gram bag of the n-gram bag, or the n-gram sequence, the 3 gram sequence for where, and then they do the same for the 4 grams, 5 grams, and 6 grams. And they learn an embedding for all of these n-grams. And what they do finally is they average over all these little embeddings. So they get a 3 gram embeddings, they get a bag of 3 gram embeddings, a bag of 4 gram embeddings, and then they average over all of these vectors, and then they take this big average to be the embedding of the word where. And the big advantage of that is, of course, it can naturally deal with spelling mistakes, right? If you spell the word length like this, where the H and the T have the wrong order, or the L comes in with three, or the word spelling comes with three L's, then for a classical word-to-vec model, if that spelling mistake doesn't occur very often, you cannot assign this word an embedding, and maybe even if it just occurs twice, then the word-to-vec model does not have enough statistics to build a reliable representation of that word. But imagine you do that based on character n-grams, so you will get that the character n-grams of spelling with 3L and 2Ls is very similar, therefore also the representation would be very similar. And this is a cool thing, especially for complex languages, right? Like German and Czech, and many of the world's languages are much more complex. Like English, that means they have many more spelling variations. So this is here now a spelling mistake, but we can also have a lot of spelling variation. Just take German verb. So it has like multiple different cases, like ich gehe, du gehst, er geht, wir gehen, ihr geht, sie gehen. So in this case it's not too many, but it's still more than English, which only has go and goes, right, in the present form. So English has very few forms, German has many more forms. The more forms we have, the less well can we estimate them, but if we base our model on subwords units like n-grams, then we can leverage the information from all of the other n-grams, right? To induce a representation for the current word. Good, so that is one thing. Then another thing is, in previous models, the question was, shall we train shall we update our word embeddings, or shall we keep them fixed? So what you could do is, you would typically feed in word embeddings to your model. And you could either keep the word embeddings all the time fixed, or you could also update them, right? Just as a simple learning process. This is also just a mapping between a one-hot vector. So you map a one-hot vector into an embedding space, so you can train this matrix also. So we could also adjust our word embeddings. And then the question is, shall we fix the word embeddings, or shall we train them on the task? And if you train them to the task, maybe you get a better performance. Sometimes you get a little bit better performance, but you also have some risk, right? And what is the risk? So let's take the following example, where where we have like three synonyms, like tele, TV, and television. So these are all synonyms. And let's say they are in our training set, and here's like a decision boundary of a classifier. So it says, well, words on this part of the decision boundary are positive, and words on the other part of the decision boundary are negative. And now let's say that TV and tele, they actually occur in the training data, but television is only in the test data. Now what happens is, if we update our embeddings, so tele and TV may be updated. They change. They change their position in the vector space. Television isn't updated, so it remains down there. So actually, they dislocate quite a little bit. They're not synonyms anymore after updating, right? So now, if television comes in, and maybe after the training, also the decision boundary changes. Now after the data has been updated, well, they change their location quite a bit. So if this word comes in, we would get a different classification than these two words up here, right? So the rule of thumb is, if in doubt, don't update your embeddings. Just leave them fixed as they come pre-trained from the internet. Good. So this is still all the bad old days with the classical word embeddings. And then in 2018, actually, But let's take another slide first. So, so in a classical sense, how would we treat word embeddings? We would treat them as follow. We have an input sentence, and we do output classification on the top, where this is a 3-class classification. We have like a sentence like German Chancellor. we would look up. So each word has an index. Then we have a lookup layer where we retrieve the embeddings for that word. So we get for each word the vector. Then maybe we concatenate all the words. So that's one possibility if you want to concatenate. So you could concatenate some local context if you want. And this is then your input to network. Then comes our hidden layer. You do a classification. So this is how you would use embeddings in a downstream task. But I think you can already think of that. So a more interesting thing is, of course, then the extension of the word embeddings that have started from 2018. And so this is Elmo. Which one? This is Elmo, and this is Bird, right? Now, they have revolutionized word embeddings because they do contextualized word representation. In each context, a word has different meaning. They are the absolute methods of choice, and actually Elmo is not. Nobody is using Elmo anymore, but Bird is. So Elmo combines 3 levels of representation. So one is character, it looks at the characters, and 2 representations are obtained from a language model, right? We've seen that already before. So we have like, we look at the characters of the word, and then we also look in the language model, 2 hidden layers in the language model. We combine that to get a contextualized representation for each word. And the language model is pre-trained on a big corpus, also for Bird. And for a new task, the weights for the 3 representations are learned to get a task-specific representation. Okay, then they have something also, I think, well, they also, like, if you have a particular task, they also learn to adapt this representation on the task. That's what we were talking already before. You could also keep that static, but they learn weights, and then they say, okay, for our case, that improves the results in many cases. But then Bird actually quickly outperformed Elmo. And Bird is actually relying on the same principle as Elmo. So the idea is it's inspired by Elmo. It says also we do contextualize embeddings. But then on the other hand, Bird has also fundamentally changed everything. Because with Bird is, well, you see, this is how Bird works. We have sentence, maybe 1 or 2 sentences come in, then they are split up into tokens. And we get, we feed these tokens, they first of all, they get some base initialization embeddings, and then they are fed through a network. In this case, it's a transformer network, a neural network. And for each word, we get several, for each token, we get several contextualized representations. But then what Bird is doing, it's not using these contextualized representations. It's not pulling them out of the neural architecture and then using them into some other model. But instead, what it's doing is it's pre-training this whole architecture on a big corpus. So we get a very good initial solution for this architecture, and it's pre-training them with a specific task. Namely, the task is masked language modeling. So it's doing language modeling, but it's doing it a little bit differently, so that it cannot take only past context into account, but also future context. But it's not so important here. So it's pre-training this whole model, and then afterwards, it's taking the very same architecture and it's just fine-tuning the architecture to solve a new task. So the idea is you have already a very good model about the English or the German or the French language or the Chinese language, and then you have a good initial solution, and then for any specific task you just modify the network a little bit to solve your specific task. And in this way, the word embeddings are not something that you can pull out, but they are in the architecture and they stay in the architecture. So this also has like fundamentally changed the way that people are using neural networks. Because before everyone was hand engineering his own network, and now people are all using the same network. Good, so this is the summary of today's embedding approaches. What do they all have in common? They are vectors and they represent natural language with a vector. And different is the unit of representation. What are we embedding? Characters, morphemes, byte pieces or word pieces, words, sentences, phrases, windows, whole sentences, whole documents. And how do we define the training? There are very different approaches. Some are more semantic, some are more syntactic, some are bilingual, some are monolingual. And how do we use them? We can use them as fixed representation for any task. So these are like a feature representation for any task. So we get a feature. Each word has a vector. That's the feature for the vector. We can feed it into a network. Or we can optimize on the task. So we can not fix them, but we can update them. And another option is well, the updating that's also done by BERT, but in a different in a different overall setting, right? We're not the embeddings of individual words are updated, but where rather the whole architecture is updated. And keep in mind the most important thing, that these embeddings that we've previously talked about, like Word2Vec, fast text, CLAV, that these are nowadays have the name static word embeddings, meaning that the embedding is always the same no matter the context, and that these static embeddings are nowadays becoming really extinct, and that they are becoming replaced by contextualized word embeddings such as those given by Elmo and BERT.